Welcome to our paper Variable Rate Allocation for Vector-Quantized Autoencoders at ICASSP 2023. I am Federico Baldassarre from KTH in Stockholm, and this work is a collaboration with the FAIR Lab at Meta AI in Paris. In this work, we focus on image compression applications of vector-quantized autoencoders, and we adapt them to allocate bitrate according to the semantic content of an image. First of all, what are vector-quantized autoencoders and how are they used for image compression? At a high level, a VQ-VAE is an encoder-decoder model trained for image reconstruction with a discretized latent space. First, the encoder splits an input image into patches and maps each patch to a latent vector. Then, the latent representation is quantized, meaning that each vector is mapped to the closest entry in a learned codebook with potential loss of information. Finally, the decoder takes this quantized representation and produces a lossy reconstruction of the image. This family of models has demonstrated good potential for image compression. In fact, it is sufficient to store the quantization index associated to each patch to reconstruct the image at a later time. If the codebook has size v, the cost in bit for encoding one patch is log v. However, this approach has two limitations. One, it is hard to scale the codebook to a large number of entries, which is necessary to capture the diversity of natural images. And two, there is little control over how much information is encoded for each patch. If we want to reduce the compression cost of an image, we can only drop uninteresting patches with an all or nothing operation. Instead, we would like to have more control over what information to retain and how much it costs to do so. To enable finer control over the compression rate, we adopt two simple mechanisms: product quantization and structure dropout. Product quantization splits each latent vector into smaller chunks and quantizes them independently using multiple codebooks. Compared to vector quantization, we now get a list of codes for each patch instead of a single one, which gives us more flexibility in choosing how much information to retain. With S codebooks of size v, the cost in bit to encode one patch is S times log v. Alternatively, we can choose to keep only a subset of the codes at a reduced cost, which enables us to control the bitrate at the patch level. But how do we know which codes can be dropped if we also want to keep the reconstruction quality high? When we drop codes from the list, we want to make sure that the ones we keep contain as much information as possible. We achieve this by adopting structure dropout during training. For each patch, we randomly mask codes starting from the tail of the list, and then we modulate the weight of the reconstruction loss according to the number of codes that remain. This way, the model is forced to store the most important information at the beginning of the list associated to each patch. In terms of compression cost, if we retain the first m codes of a patch, we will need m log v bits for the codes plus a small overhead of log s to store the number m itself. An advantage of training with product quantization and structure dropout is that a single model can be used across a broad range of compression rates instead of training a specialized model for each desired operating point. We can analyze this property on the rate distortion curve that plots the structural similarity index against bits per pixel. The orange dots indicate the performance of three separate models that were trained without structure dropout and therefore can only operate at a specific rate. The blue line indicates the reconstruction performance of our model for different rate budgets. At each operating point, the budget is allocated uniformly by selecting an equal number of codes for all the patches. We observe that our model performs well across the whole spectrum of compression rate, with only a small penalty compared to single rate models. After training, we can allocate the rate budget uniformly across all patches, as done in the previous slide. Even better, product quantization and structure dropout allow us to adapt the compression rate on a patch-by-patch basis, for example, based on its content. we use the attention map of a pre-trained Dino model as a proxy for saliency estimation that requires no external supervision. These models have been shown to learn strong features that correlate well with human perception, and therefore are a good choice for semantic compression. Given an image, its Dino saliency map, and a rate budget, we choose how many quantization indices to keep at a cost of log v bits per code per patch. Additionally, we need to store the number of selected codes, which takes log s bits per patch. Here is an example to compare uniform and semantic rate allocation. For the image on the left, we keep the first 7 out of 32 codes for each patch, resulting in 0.23 bits per pixel. For the image on the right, we use the saliency map from Dino to determine which patches should be given more bits while also matching the rate budget. The two heat maps visualize the actual cost for encoding each patch using the codebook frequencies from the product quantizer. Red indicates a high number of bits, and blue stands for a low encoding cost. Comparing the two images, we see that semantic rate allocation reconstructs the main subject better, while some background details are sacrificed. To quantify the effect of semantic rate allocation presented in the previous slide, we compute the Fréchet inception distance at different rate budgets. Given a large dataset of images, a low FID indicates higher perceptual quality, as opposed to metrics like MSE or PSNR that focus on pixel level differences. This plot shows that using Dino to control rate allocation at the patch level is better at preserving semantic content, and that the difference with the uniform allocation strategy is more pronounced at the lower rates. Thank you for attending this presentation on variable rate allocation for Vector-Quantized Autoencoders. Join us at the poster session to know more about this project.